In this video, I'll go over the basics of parametrizations and calculus. So a parametrized curve, x is equal to a function of t and y is a function of t, is called differential t if f and g are differentiable at t. Now, as you imagine the curve, if this is a point on the curve, as time moves forward, notice that my curve is being traced from right to left. But if you focus at one single point, and therefore one single moment in time, there is a certain amount of change in y and a change of x. Here the change in y in time, at this time, is positive, and the change of x in time is negative. Notice though that there is a slope to the curve, and you should expect then that the rate of change of y in terms of x should be related to the rate of change of y in terms of t and the rate of change of x in terms of t. And as long as that the functions are differentiable, x in terms of t, y in terms of t, and y in terms of x, then they are all related by this equation. So we get this really nice result. If we assume that a parametrized curve, x is a function of t and y is a function of t, is differentiable at t, and the derivative of x in terms of t is non-zero at t, then y is a differentiable function of x for that time, and the derivative of y in terms of x is just the division of the two derivatives, the derivative of y in terms of t and the derivative of x in terms of t. Now notice that the way I'm choosing to write it is that the derivative in terms of x of y. So if y is a function of t and you're doing the derivative in terms of x, you take the derivative of the function of t in the numerator and take the derivative of the x in terms of t in the denominator. That helps explain how to find the second derivative by doing the exact same thing. To take the second derivative of y in terms of x, you think of it as taking the derivative in terms of x of the function of t. Remember, the first derivative is a function of t right now. So you just take the derivative of that function of t in terms of t and divide by the derivative of x in terms of t. And that's how to find the second derivative. For example, let's go find the tangent to the curve x equals the secant of t and y equals the secant t, where t is between negative pi over 2 and pi over 2. But we want to find the tangent at when t is pi over 4. So to do so, the derivative of y in terms of x would then be equal to the derivative of y in terms of t divided by the derivative of x in terms of t. Now the derivative of y in terms of t, that would be the secant squared of t, and the derivative of x in terms of t is the secant of t tangent of t, and I can simplify that to be just the cotangent of t. So when t is just pi over 4, the rate of change of y with respect to x when t is pi over 4, that would be the cotangent of pi over 4, and that's just 1. That gives me the slope of my line. But to find the point of the line, I need to know what is x then for that particular time. I need to know what the y value is for that particular time. So the x value is the secant of pi over 4, which is the square root of 2, and the tangent, that's the tangent of pi over 4, that's our y value, and that's just 1. So the equation of the line is y minus the y value is equal to our slope, which is 1 times x minus our x value. And you can then come back and just make that look nice by just solving for y to get y equals x plus 1 minus the square root of 2. And that's it. That would be the line tangent to the curve at that moment. Doing that again, let's go find the second derivative of y in terms of x. Now the answer will be in terms of t when I'm done. So we first must find what's the derivative of y in terms of x, and that would be the derivative of y in terms of t, all over the derivative of x in terms of t. So the derivative of y in terms of t is just 4, and the derivative of x in terms of t is 2t. So that simplifies nicely to be 2 over t. To find the second derivative of y in terms of x, think of it as the first derivative of the first derivative of y in terms of x. So I need the derivative of the derivative in terms of t, and then I need the derivative of the x in terms of t. So we already have right here the derivative of y in terms of x. I need to take its derivative in terms of t and put it in my numerator. That would then be a negative 2 over t squared. The derivative of x in terms of t, that's just 2t. And simplifying that, that gives you negative 1 over t cubed. And that gives you then the second derivative at all times. Incidentally, notice then that since time goes from negative infinity to positive infinity, I could even tell you the times over which the graph would be concave up or concave down, because this still gives you the concavity. So I could say then that if t is bigger than 0, the graph will be concave down. And that's since the second derivative over that time would be negative. Because if this is always positive, then the product is always negative. And you can get a similar result to find out when the graph is concave up. It's sometimes useful, though, to talk about how a point is moving along a curve. And sometimes curves approach another point, like a path leading into a place. And we need some way to say what that means. So we'll say a differentiable curve characterized by x as a function of t and y as a function of t is said to approach a point x naught y naught as t approaches t naught if the limit of the point on the curve as it moves goes towards the point we're approaching. Now, you have to be careful. All this really means is that you have a point out there. All this really means is you have a point in the plane. And for that point, there's a path. Now, this path is the curve that I was discussing. And as we move along it, the point x comma y gets closer and closer to this one point in the plane. It doesn't mean the path goes into it. It just means that if you imagine any kind of little open region around that point in the plane, that the path eventually gets inside of that and never leaves as t gets close to t naught. So it's perfectly possible for the curve to not go into the point. It just kind of gets trapped in a bubble where the bubble can be as any size as you want, and all you need to guarantee is that if the bubble is a certain size, that the t just needs to be close enough to t naught so that the path is always inside that bubble for those times near t naught. Let's consider the second case. We say that the curve enters the point P as t approaches t naught if this limit exists, or that it's infinite. Now, this is supposed to mean, imagine like here's the point, here's the curve that is approaching this time that point. To enter the point means that if you look at x naught comma y naught and you pick the point x comma y that's changing in time, as this point moves towards this one, if you look at the line segment that connects the two, that line segment has a slope. That is what this is. It's just a slope between these 2 points. I'm insisting, therefore, that that slope approaches something. So to say that the path enters the point, that means as the path gets near that point, you get to a well-defined, kind of like a tangent line from one side, that you come in at a certain slope. To show you an example or two, the curve x equals 2t and y equals t squared approaches and enters the point 0, 0 as t approaches 0, because if you look at a point on the curve as time passes, as t approaches 0, the point x comma y approaches 0, 0. And if you look at the line segment between the point that's moving on the curve as time changes and the point 0, 0, that as t approaches 0, that limit's also 0, so that you have a well-defined slope. In the picture, the blue line, that slope, becomes more like the slope of our tangent line, the slope of 0. So you come in at a certain direction. Let's consider another example. The curve x equals e to the negative t times cosine of t y equals e to the negative t times sine of t approaches but does not enter the origin as t approaches infinity. Because if you look at a point as it's traced out, it will be a spiral going counterclockwise, but the limit of both the x and the y component of this point as time approaches infinity will go to 0, because the sine and cosine are bounded, but e to the negative t goes to 0 very quickly as t goes to infinity. So the point on the curve approaches the origin as time increases without bound. But the limit, though, of this ratio, that corresponds to the slope of the line that's formed as the point x comma y moves, and notice that in the spiral, that blue line will constantly rotate in a counterclockwise fashion, so it will never settle down to any slope at all. So, in fact, as you can see in the limit does not exist. So, this is an example of a curve that gets close to something, it approaches something, but it's not considered to enter it. We have enough now to talk about how to find area. We'll do it the same way as always. We'll think about taking a region. In this case, I'm looking at the region between the curve, my parametrized curve C, and the x and y axis. So I want to find the area that's inside this region. Now to do so, I'll think of it as taking the x-axis. I'll crush the object down to the x-axis, give me an interval. And on that interval, I'll partition it into small pieces to get a very, very small change in x. And then I'll find the corresponding point on the curve, which will give me the height, which is the y value. So the area of this rectangle would be y times dx. So I would integrate from the first x value, x0, to the last x value, x1. Now, you have to be careful with what I just did. Notice that in this case, that the derivative of x in terms of time is actually always positive. So for a positive dt as time moves forward, you would get a positive dx. So this dx is always positive in the interval that I'm interested in. So this seems right. I'm adding up positive areas. What if I did the same thing here? Notice the bounds now are in the other order. Why? Well, what if you were to do the same thing? We'll want to find the area of this region. To do so, I'll crush the object to the y-axis, creating an interval. I'll then partition it. I'll get a very small change in dy. I'll find the corresponding point on the graph, and the distance from the axis to that point would be the x value. So the area would then be x times dy. I would then sum up all those pieces. So then why are the bounds in the other order? Well, the reason is this, is that what we're going to do is we're going to replace everything here with time values. Okay, we're going to replace all of this with time values. This is a time when this happens. This is a time when this happens. So notice that in the picture that the derivative of y in terms of t is actually negative. As time passes, the graph is always going downwards. So for increased value of time, you get a decreased value in y. So this product is actually always negative. It's always negative. That's why the numbers are in the wrong order, because I should be integrating from y0 to y1, smaller to bigger, smaller y value to bigger y value, of x dy, but I have to put a minus in front to compensate for that. So there's a few little tricks then we have to be careful of when we're looking at area. First one is just when you find the integral, you're going to change everything over to t. You're going to basically use a substitution. Replace x, y, dx, and dy with what it's equal to in terms of t. Change the bounds also in terms of t. Then, just be aware of how, as time increases, how the change in time affects dx and dy. Is dx always positive? Is dy always positive? If so, then you're fine. If not, then you have to compensate for that in the integration. Also, it's understood that as the curve is traced out, the point doesn't retrace the curve more than once, because it's possible this is a loop and you might generate the same curve multiple times, or God forbid you might go backwards somewhere and then go forward later, canceling and adding area again as you go. Let's do a small example. I want to find the area enclosed by this y-axis and the curve given parametrically as you see here. So to do so, to find the area that's inside here, I'll think of it as partitioning the y-axis. So I need to know that point, I need to know that point. And then I'll break it into small pieces, so then this will be my dy, and I'll find the corresponding height to get a representative rectangle. Now the area of that rectangle should be the x value of that point times the thickness of the interval, which is dy, and then I would sum up over all those pieces over the times that are necessary. Notice what's happening. So let's find out when we're here and when we're at that point. To do that, that only happens when the x coordinate is 0, because that's when the point would be at the y-axis. So let's go ahead and find when, for what times will the x coordinate be 0. Clearly that means then t times 1 minus t is 0. So that's a 2 times. T is 0 and t is 1. Now when t is 0, you get the point 0, comma, 2. So this is the point 0, comma, 2. That occurs when t is 0. But when t is 1, you get the point 0, comma, 1 plus e to the negative 1. That's 1 plus 1 over e. That's this point. That's when t is 1. So if I just integrate what you have right here from the y values that we're interested in, we'll probably get a negative answer. The reason is that as time is passing, notice that dy dt is actually equal to negative e to the negative t, and that's always less than 0. So as time increases, the y decreases. So this is actually always negative. I'd be multiplying a negative number to a positive number. Now to set up the integral correctly then, I'll change everything over to parametric equations. So I know what x is, it's just t minus t squared. And I know what dy is, because dy would have to equal negative e to the negative t dt. So I would have here a negative e to the negative t dt. And for the bounds, you can think of it two ways. You could think of it going from 0 to 1, but then the answer is negative, or you can think of it from 1 to 0 and then it's positive. Because if it's 1 to 0, you're going backwards in time, and in that case the change in y is always positive. I'll just do it this way. So let's just do that integration. The double negation then cancels, and we get the integral from 0 to 1 of t minus t squared times e to the negative t dt. Just to check it, notice that over this interval, this quantity is always positive, and this quantity is always positive. So I'm adding up positive areas. This now makes sense. To do that integral though, we need integration by parts, and I'll do it multiple times. So I'll use the tabular method to make my life a little easier. You have plus and minus here. You'll have your u, and you have your dv. So I have a plus, and then t minus t squared, and e to the negative t. You have a minus, a 1 minus 2t, and an e to the negative t with a negative in front. Then you have a plus, a negative 2 times e, well, not times, but and e to the negative t. And then lastly, we'll have a minus, a 0, and a negative e to the negative t. So doing parts multiple times, I would get t minus t squared times a negative e to the negative t. And then I'd have a minus 1 minus 2t times a e to the negative t. And then I have a plus, a negative 2 times a negative e to the negative t. And then I have finally plus c. This should be the antiderivative. Now I'll just evaluate this thing from 0 to 1. Before I do that, though, it seems reasonable to take out the common factors because there's just so many of them. So I'll factor out a negative e to the negative t. To do so, taking that out of this, you get t minus a t squared. Taking negative e to the negative t out of this, that will give you a plus 1 minus 2t. Taking this out of that, you get a minus 2. This is still all evaluated from 0 to 1. That is negative e to the negative t. I'd have a negative t squared. I'd have a negative t, and I have a negative 1. And I evaluate that thing from 0 to 1. And it looks like I should not have factored out the negative. Oh well, that happens. So then this would then be, if you plug in 1, you would get a e to the negative 1. And then this would all be negative 3. The negative 3 times the negative e, that'd be a 3. And if you plug in 0, you get minus a negative 1 times 1. So that would then be minus 1. So again, if I plug in 0, that's a minus 1. And that would then be a minus 1. That's 1, and I subtract it. That's the answer. That should be the area of the region. It'd be, in the end, 3 over e minus 1. And that is close to 0, but it's still positive. Let's now tackle the issue of arc length. Let C be a curve characterized as normal. X is a function of t, and y is a different function of t over an interval from a to b. Further assume that f and g are continuously differentiable. That means then their derivative is continuous on the interval. Also, let's assume that the derivatives are actually never simultaneously 0. Such curves that are continuously differentiable and never simultaneously 0, for when the curve is defined parametrically, the curves are called smooth. It's just a way for us to guarantee that as the point traces out our curve, that the curve never stops, the point never stops anywhere, and that the graph can't have a cups and it can't have a corner anywhere in that graph. To find the arc length, let's subdivide the curve into n segments separated by points p0 through pn, where p0 is understood to be the initial point A and pn is understood to be the terminal point B. So we have that these points correspond to increasing time values, t0 through tn. So if you want to approximate the length of the curve, it's equal to the sum of the lengths of the segments formed by going and connecting two consecutive points. But we know how to find the distance between two consecutive points. It's just the distance between points. We take the square root of the sum of squares of the difference in the x coordinates, that's the f's, and the difference in the y coordinates, that's the evaluation of the g's. For notational sake though, let's just write the change in y being squared and the change of x being squared, so we don't have to look at the functions themselves. Since f and g are continuous and differentiable on the entire interval from a to b, they're continuous and differentiable on each of these subintervals of time. So look at the kth subinterval. In that interval, there are two numbers, c sub k star and c sub k double star, so that the change in x over the kth interval is just the derivative of f evaluated at some number, we don't care what it is, times the change of time, and the change in the y value over that subinterval is just the derivative of g evaluated at some number, we don't care what it is, times the change in time. That means then that the overall length, being the sum of the length of the segments between two consecutive points, is the sum of the squares of the changes in the function values, but that is equal to the sum of the squares of the derivatives of these functions evaluated these two different choices, each then multiplied to the change in time, and that sum of squares is square rooted. Notice though you can take out the common factor of the change in time squared, giving you this summation. Now, this is important because that's a Riemann sum. No, almost. It's not really, actually. If it was a Riemann sum, then the change in the variable would be multiplied to a single expression that's a function evaluated at only one number. This is evaluated at 2, but actually it's okay, is since the change in time is getting really small, these two values are getting really close to each other, and the limit, it can be shown that the limit of this exists and actually equals a definite integral. That gives us this nice result. If you have a smooth curve parameterized by x as a function of t and y as a function of t over some interval, and as long as it's traced out exactly once as t increases from a to b, then the arc length is given by this integration. And I've given it to you in a more differential form. This should look reminiscent to something you saw before in Calc 2. Let's go use that to find the perimeter of a circle. Now you all know the perimeter of a circle. It's just the circumference. But let's do it using parameterizations. So one parameterization of a circle would be x equals r times the cosine of t, and y is r times the sine of t, as I've shown you earlier. Here the parameterization's interval would be from 0 to 2 pi. That way I go through the circle only once. That I stop at the same place I begin is fine, because I don't get any additional perimeter for a single point. Well, by the formula then, the arc length should be given by should then be equal the integration from 0 to 2 pi of the square root. I take the derivative of x in terms of t, which is negative r sine of t, and I square it, and I add. I take the derivative of y in terms of t, which is r cosine of t, and I square it, dt. That's the integral I have to do. Luckily, this is very easy, because this is really the same as writing r squared times cosine squared of t plus sine squared of t. And we all know that this is 1. So it's 1 times r squared. So it's just r squared. And that's inside of square root. So it's the integral from 0 to 2 pi of r dt. That is rt evaluated from 0 to 2 pi. And that is 2 pi r. That's the answer. That's the circumference of the circle. Now it's convenient to note that for each time, if you start at the initial point of the curve, that there's an association between the time and how far you've traveled. So to find that out, think of it as you're starting at a point, you have then some curve, you then end up a point, and that's at x comma y at a certain time. But then that means there's a certain distance you traveled to get there. So there's an obvious association, if you have a certain initial point where you begin the path, between the distance you travel and how far it's gone. So there must be a function there. And this is it. It's just the arc length formula, where you go from the beginning time a to some ending time t, where t can be any value after the time of a. And you just do this integration. Notice the integration has the variable of z, because I can't use t. I can't use t as the variable that's changing and also as a bound and therefore constant. By the fundamental theorem of calculus, though, that means that the derivative of s in terms of t, the rate of change of length in time, is given by the sum of the squares of the rates of change of x and y, where that sum is then square rooted. Now, if you multiply both sides by dt, kind of abusing notation, you get that the arc length differential, ds, is given by this particular product. This is really useful. This way we can talk about partitioning paths later on in life, and we'll even do it in an example next. Also, do you see how the inside has kind of like a division of dt squared and the outside has a dt? They kind of cancel, and we like to remember the result this way. That way this gives us a nice simple way to relate ds to other things. But oftentimes x and y are in terms of t, and we'll just use this substitution right away to go convert the ds in terms of the parameter t. Let's use this to find the centroid of the first quadrant arc of the asteroid given by x equals cosine cubed and y equals sine cubed. So we're focusing only in on the curve that you see right here. Just that little bit. Now notice for that portion of the curve, that the curve appears to be symmetric about the line y equals x. Because of that, we expect that the overall average value of x and the average value of y has got to be the same thing. So we expect that the centroid, that in this case these are equal to each other because of that symmetry that we see along that line. So what we have to do is just compute one of them. We'll automatically get the other. To do so, I need to know first the total amount of mass. So the mass, you can think of it as summing up all the small bits of mass as you move along. Well, now the mass should be given by 1 times ds, because you think of it as a unit weight of 1 times the arc length. So the arc length times that weight, that'd be 1 unit of mass. So all we have to do is really integrate this thing here. And that would then be the integration of, well, ds though, that means I partitioned the arc length. Let's instead convert that over into times of t. So we know what ds is. It's the square root of dx over dt squared plus dy over dt squared dt from the beginning time to the end time. That should then for me add up all the masses. Notice that this is positive as time passes, and this is certainly positive. So going from a lower time to a higher time, that seems reasonable. So I have to do the integration from 0 to pi over 2 of the square root of, I need the derivative of the x in terms of t. That would be 3 cosine squared of t times sine of t, and I have to square that. And then I add, you would get the 3 times the sine squared of t times the cosine of t. I have to square that dt. So that is the integral that I have to somehow figure out how to smash out. But notice it's really not that bad, because just carrying the integration way over here, that's the same as saying 0 to pi over 2 of the square root. Notice that this and that has a common factor of 3 squared, of a cosine squared, and of a sine squared. If you do that, you would get 9 cosine squared of t, sine squared of t, and what's left over, well, if you take this product out of this factor, the only thing you have left is a cosine being squared. So that's cosine squared of t. And for the same reason, this would then give you, in the end, only a sine squared. So you get sine squared of t, and that's times dt. Well, this is 1, and since these are all squares, when you square root them, they all cancel because they're all positive terms for this angle range. So you just get the integration from 0 to pi over 2 of 3 cosine of t times the sine of t dt. And that is 3/2 the sine squared of t from 0 to pi over 2. If you plug in pi over 2, you get 3/2. If you plug in 0, you get 0. That's the answer. That's the math. Now, without repeating myself throughout all this integration process, you could also find the moment relative to the y-axis, as that's just the integration of x dm over the range of masses that we're adding up. But that is the same as x ds, because here dm is ds, because it's just, in this case, a centroid. We're assuming a constant multiplication between the length and the mass. But we know what ds is, so I can turn everything over in terms of parameterizations to get from 0 to pi over 2 of x times the square root of dx over dt squared plus dy over dt squared dt. Now I'll leave the details for you. Just replace x and y and their derivatives in this mess. You'll get an integral that has a power of cosine and only one factor of sine. So it's very easy to integrate, and when you're done, the answer would wind up being 3/5. So if you want the average x value, which is the same as the average y value, which is, in the end, these are the coordinates for the center of mass, the centroid, you just take the division of the moment with a relative to y, divide by the mass. So that's 3/5 divided by 3/2, and that would wind up being 2/5. So the center of mass is at 2/5, 2/5. And that's how this problem would be done. Lastly, you probably remember that the way we found surface area is we found the arc length first, and then we just revolved it by using a fulcrum in order to go get the answer. So to find the surface area, if you revolve around the x-axis or the y-axis, it's the same thing I did before. It'd be the integration, technically over the arc length, of 2 times pi times y times ds. Just remember what ds is as the arc length differential. Or if you want to go around the y-axis, it would then be 2 times pi times x times ds. And again, just remember what ds is as the arc length differential. It's very similar to the problem you just saw, so I won't go through an example. And that gives you a basic introduction between parametrizations and how we use them with calculus to find tangent lines or slopes, or to determine how points are moving, or to find areas of boundary regions, or to find arc length or surface areas. It's very similar to what you saw before. It's a little bit more complicated.